thanks for the organizers and for having me here to talk in London. It's really great to be back here. And yeah, so I'm going to tell you about how to do a fault-tolerant non-Clifford gate for the surface code in 2 dimensions. So I expect I don't need to tell anybody here what a non-Clifford gate is, but just in case, lately I like to liken it to the divide button of a pocket calculator. So if you like, imagine a calculator, but the divide button is removed. You have add, subtract, and multiply, and the digits. You don't get the decimal place because that's really just divide by 10. And well, with those 3 functions and those 10 digits, all you can ever do is hit the integer numbers. There's no operation that will take you out of the integer numbers. And well, sometimes it's nice to do calculations with all the reals. For example, most of the probabilities lie in between 0 and 1. Sometimes it's nice to calculate with those. So to start approximating real numbers, what we need is a divide button. And in the same way that the divide button lets us hit all the numbers in between the integers, a non-Clifford gate lets us hit a whole bunch of quantum states that we can't hit with just the Clifford operations. So that's really important. And in fact, we know that due to the Gauss-Nil theorem, that you're never going to surpass a classical computer if you only have Clifford operations. So that's why we need one of those. OK, and it would be really nice to do it with the surface code. We've heard a lot of talks about the surface code. Everybody wants to build it because it has low-weight parity checks. And what's more, it's 2-dimensional. And some architectures in particular are limited to 2-dimensional architectures. So I don't really think I need to spend too much time. I don't really have too much time to tell you what the surface code is, but it's a 2-dimensional model with qubits living on the edges. I'm going to put the qubits on the edges throughout my talk. People put them all over the place these days. But OK, it has a star operator, which is the product of Pauli x's on the edges touching a vertex, and a plaquette that's the product of Pauli z's on the edges that bound a face. And it has logical operators of z's that run from top to bottom, and x's on the dual edges that run from left to right across the lattice. And OK, I don't want to talk too much about the stabilizers. I'm going to use the microscopics a little bit, but quite a lot of what I'm going to tell you is just understanding a macroscopic picture of the surface code. So really, a lot of the time, I'm going to just draw the surface code like this, where I haven't drawn the lattice, the qubits in the middle of the lattice. But what I have drawn, which are important, are rough boundaries, which terminate the Pauli z logical operator, and the smooth boundaries, which terminate the Pauli x logical operator. I'm going to be talking like this quite a lot. OK, so we've been pretty good at doing the Clifford gates with the surface code. The first proposal for these were in the Dennis paper. They had a way of doing. Oh, OK. They proposed some ways of doing some Clifford gates. And then for a long time, Rausendorf, he showed us how to put punctures in the surface code, or the measurement-based topological cluster state model, and do Clifford gates that way. And we've steadily improved. So like over time, as Andrew was asking in his question just earlier, we came up with twists. That was an invention of Hector Bombin, and lattice surgery, which was in this Horstman paper. So last QEC in Maryland in 2017, I gave a talk really unifying all of these twists and lattice surgery and puncture braiding. You can read about that here in this paper, or I think you can find the talk online. And with the Clifford gates, that's enough. If we have some noisy state injection, we can do magic state distillation. And if I get to the end of my talk, I'm sure I will, I'll say a little bit about magic state distillation. But yeah, we need a non-Clifford gate as well. So I'm going to propose a way of doing that. Now, I said it's a 2-dimensional result, and it is a 2-dimensional result, but to understand how this gate works, you have to think in 3 dimensions quite a lot. So a lot of the reason this gate works is because of a property the 3-dimensional surface code has. So the 3-dimensional surface code is just like the 2-dimensional one. It has a star operator of Pauli X's touching the edges, touching the vertices of some lattice, and plaquette operators, which are the product of Pauli Z's on the boundary of a face of some three-dimensional lattice. And like in the 2D case, I really want to talk about just rough and smooth boundaries. So here we have, you can see by the dashed lines, rough boundaries on the left and the right side of this block, macroscopic block of three-dimensional surface code. And the logical operator here will be the product of Pauli Z's running from the right to the left and terminating on the rough boundary. And it also has a Pauli X logical operator, which is a membrane, two-dimensional membrane-like logical operator that terminates on 4 smooth boundaries. Okay, and yeah, so as I said, the three-dimensional surface code, unlike the two-dimensional one, it has a transversal non-Clifford gate. So a transversal gate, again, I think we all know, is where you perform a local rotation on the physical qubits to make a and this will preserve the code space. Was that me? So this will rotate the code space and leave the rotate the logical qubit in the code space while leaving the code preserved. And in particular, if we the transversal gate the 3D surface code has is the transversal control Z, where if we take 3 copies, it's a 3 qubit gate. So if we take 3 copies of the surface code, and we perform a CCZ gate between the qubit at location P of this code and the qubit at location P of this code and the qubit at location P of this code, then we perform a logical CCZ. And so what's important, in fact, this is going to become a problem later that we'll fix. The surface codes are all differently oriented, so this one has rough boundaries on the top and bottom, this one has rough boundaries on the left and right, and this one has rough boundaries on the front and back, so they're all rotated by 90 degrees. So the lattice I'm using is that of, in this paper by Michael Vassmer and Dan Brown here at UCL. And in fact, they're not all cubic lattices. 2 of these codes have to have this lattice geometry. I don't want to focus too much on the microscopics, though. The other one has a standard cubic geometry. That's right. So, okay, the 3D surface code has some properties that we want, but the one we don't want is that it's 3-dimensional. So what we have to do is we have to connect the 3D surface code with the 2-dimensional surface code. So, okay, one thing they both have in common is that they both have rough and smooth boundaries. So in fact, what we can do is we can find a 2-dimensional surface code in the 3-dimensional surface code if we take some plane of qubits where that plane has 2 rough boundaries, or it crosses 2 rough boundaries and 2 smooth boundaries. So this dark gray plane here would be suitable to find a 2-dimensional surface code. And in fact, we can convert between the 3-dimensional code and the 2-dimensional code by measuring all the qubits that are that aren't a part of the 2-dimensional surface code, but are a part of the 3-dimensional surface code in the plus state. If we measure all the qubits in all this white space and here in plus, we collapse the 3-dimensional surface code onto a 2-dimensional surface code and preserve all the logical information. So that's going to be important. Likewise, we can reverse that operation. We can start with a 2-dimensional surface code, like this gray one here, initialize all the qubits in the white space in the plus state, and then measure all of the plaquettes of the 3-dimensional surface code, and that will almost, I have to add a little more in a couple of slides' time, but that will almost give you the 3-dimensional surface code if I do just that. Okay. So this is going to be a trick to reproduce a 3-dimensional surface code over time with only a 2-dimensional array of qubits. So what I just described to you is a dimension jump, where we go from a 2D surface code to a 3-dimensional surface code, and a 3-dimensional surface code back to a 2-dimensional surface code. But in fact, we don't need all L by L by L dimension of the 3-dimensional surface code to do this trick. We could, for example, take just produce a small L by L by like 2-ish slice of 3-dimensional surface code, and then collapse it back down. And to back to the two-dimensional slice. And with this, we can use a two-dimensional slice of qubits to reproduce a whole three-dimensional surface code in kind of an accordion-like way. So you make a small piece of 3D surface code, and then you collapse it onto a two-dimensional slice. Then you produce a small three-dimensional slice. It's 2D, but it's just a thin slice of 3D code, and then you collapse the qubits back down onto a two-dimensional slice. So it's kind of moving along like an accordion to reproduce a whole three-dimensional surface code over time. So this is going to be the trick we're going to use to find a CCZ gate. We're going to, switch pen. We're going to reproduce a three-dimensional surface code with a two-dimensional array of qubits over time using these small little dimension jumps. So if you're familiar with the Rausendorf model, this isn't really such a new idea. There, they imagine this fault-tolerant quantum computation with a cluster state model. But to do this fault-tolerant quantum computation with the cluster state, you only need to produce a two-dimensional slab of it at a time, and you keep producing this three-dimensional model on the fly. This was exploited by Hector Bombin, I should say, to also reproduce a three-dimensional color code over time, and I'm using a lot of the tricks that he uses in this paper to get this result with the surface code. Okay, so here's the thing. I said to you before that we can go from a two-dimensional surface code to a three-dimensional surface code, but that wasn't quite true. It's almost true, but it's not quite true. So in fact, if we start with some piece of two-dimensional surface code and we produce a three-dimensional surface code with that, well, when you measure the random plaquettes, you don't get the, you get a bunch of random outcomes. They can give you plus or minus one outcomes as you like. And well, that seems like a problem because in fact you need to have all of your plaquettes in the plus one eigenstate to do the transversal gate. However, it's quite easy to error correct. We have to do a trick called gauge fixing. So in fact, what, we have to do some recovery to get all the plaquettes in the right eigenstate, which involves applying a Pauli X operator somehow. But it's quite easy to do. So in fact, the thing is, these minus one outcomes that appear, they'll all appear in loops. And the reason for that is the plaquettes, they have to respect constraints around each cell of the lattice. Now, you can see that if I took the product of all of the Pauli Z terms on all the faces of this cube, they have to give identity. So that means there has to be an even number of minus one outcomes around the boundary of every single cell. So then if you look back on the macroscopic picture and you regard these minus ones as a small segment of a string on a dual lattice, well, all of these little strings have to form closed loops. So the error correction process is really just you find a Pauli X that lives inside these loops. So we have to do this if we want to do this CCZ gate. However, this could be a bit difficult, as we're going to see. We're going to solve this problem, but it's difficult because we need to do this error correction step without having access to the full three-dimensional code in one moment. We have to do it bit by bit. Okay, so this is what I've said so far. We're going to reproduce a three-dimensional surface code with only a two-dimensional array of qubits over time using small dimension jumps. We have to gauge fix that. So we have to make sure all the plaquettes are in the plus one eigenvalue, even though when we measure them, we'll get a random outcome. And we'll do that even if the measurements are noisy, in fact. And the reason we're going to do this is because we want to produce a control phase gate. Okay. So there's an issue. So as I said, if we want to move a plane through this block, the plane has to include two rough boundaries and two smooth boundaries. So that limits the direction you can move the plane in. So for example, what we could maybe do is take, so these two codes in the middle and the right, they have rough boundaries on the middle, on the sides, so we could choose a time direction upwards. But we don't get to do that on this one on the left because it's got smooth boundaries on all of its sides. So we're forced to pick a different time direction, which is a little bit annoying. And that's a problem because I need to interact all the qubits of all these three blocks. So for example, let's compare these two. Here's a code with the time direction moving upwards, and here's one with the time direction moving rightwards. And, well, over here, this qubit of this two-dimensional plane is expecting to interact with a qubit over here of this two-dimensional plane. But I haven't made it yet. I haven't made that part of the three-dimensional surface code. So I would have to move this one along to here, but then that would be a problem because these qubits over here need to interact with this plane up here. It's a big mess. And so we have to be a bit more careful about how we move these planes around. And, well, luckily what we can do is we can just tilt all these planes. And this makes everything work out. So in this picture, you can see, so two codes can move upwards, as I showed you in the last slide. And so two of the codes are going to be here, but I'm only going to show one because they can move in parallel. And I have another code that's going to move from left to right, because that had to move from left to right. And what I've done is I've tilted those planes. That's OK, because all of these planes still have a little bit of rough and a little bit of smooth boundary, so I can still produce a small bit of three-dimensional surface code and still keep a small piece, well, a regular piece of two-dimensional surface code as I go through these code deformations. But because of the angle, when they meet in the middle where I'm going to do this CCZ gate, well, they're all going to have, all the qubits are going to be alive at the right times for this to all work out. So in fact, I was really reluctant to make this, but I explained this to about 3 professors, and after 3 professors ask you to make an animation, that's what you do. So this is what's happening. They didn't tell me to embed it in my beamer, though, so I have to switch. So this is what's happening. This is a two-dimensional projection. Here I have 2 codes of this blue code moving upwards in time. Here I have another code moving from left to right. And they're filling out this two-dimensional block, which is the three-dimensional block where I'm doing the CCZ gate. And you can see that all the qubits are overlapping at exactly the right time. So what's actually happening here? Well, like I'm using time to reproduce the 3rd dimension, so this isn't really what you'd physically see. What you'll physically see is, look, this is really good. What I can do is I can collapse it. All that's actually happening is one code is moving from left to right over some static blue code. So the reason it works out like that, let's just go back one more time, is because, well, so these 2 blue codes, they're reproducing the y-axis with time. This green code, this is reproducing the x-axis over time. So if you collapse the time, well, which I'll collapse in the y direction, well, the blue one stops moving. The only one that's actually moving is this green code. It sweeps across the other 2. So I'm going to go back to my slides now. And so in this, I'm going to try save a little time and not tell you about this one, but you can find this picture in my paper. This is exactly what I showed you before, where I start with a 2-dimensional code. I produce a thin slice of 3-dimensional code, and then collapse it back to the 2-dimensional code. And meanwhile here, I'm doing the CCZ gate at this time, t1/2. And so this is how it looks in the 3-dimensional picture with microscopic. Like I've even drawn the qubits on these little gray planes, so you can see everything. And here's a cartoon of what it is. I showed you this when I collapsed the code, where there were 2 codes just sliding out, well, 3 codes, two static codes and 1 third code sliding over. This is a cartoon strip of how you'd expect this gate to work. You would have some apparatus, like 3 stacked arrays of qubits, or they don't have to be stacked. I haven't really figured out how to arrange these qubits in the lab, but it's kind of nice to think of them as overlapping chips. So you would need this one long chip. If you're strictly 2D, you could actually make this cylindrical and save a lot of qubits if you have some modular architecture. And you copy 1 code on over here, and the other 2 codes live on these little static islands. And what you see is these black qubits are the code passing underneath, where you're doing CCZs in between these 3 stacks of the chip as the code passes underneath. And what else do I have to say? Right, so again, I've only told you half of the story because while I was doing all these measurements, I was getting random outcomes with my plaquettes. And that's already kind of bad because I have to figure out how to correct my plaquettes as I go, but I only have a 2-dimensional slice of code to do this correction. And what's more, there are going to be measurement errors. I haven't even talked about any errors yet. And this has still got to work if some of my measurements are faulty, so some of my measurements are going to go wrong. So let's do an easier case first of all. I'm just going to imagine producing a piece of three-dimensional surface code, forget 2 dimensions. And I start with all my qubits in plus, I measure all the plaquettes, and I get some random configuration of loops. So I'm supposed to get loops like this, but if there are measurement errors, then I'm going to see small segments of string that are going to terminate in the wrong places. They're not supposed to terminate, remember, because of the constraints about the cells. So here I have an error. Here's an error. It's a bunch of string segment errors, and I can see the error by the endpoints. I'll call these endpoints defects. And I know that some errors happened in between all of the defects that you can see, and you can see them because you can see the string is broken. So, so what am I going to do? I've got to fix this up. So what I'm going to do is I'm going to run error correction, and I'm going to try and predict what errors cause those 2 defects to appear. But I might make a mistake, and this is a problem. It's not even okay just to be like topologically equivalent to the error. It's actually got to be exactly the same as the error. So let's say I predicted this to be my correction, this light gray line. Well, then I'm going to apply a bunch of Pauli X corrections to fix the gauge of this model. And so over here, this was just a regular loop I was supposed to correct, so that all went away. But because of this measurement error, and the correction was a little bit wrong, I left all of these little Pauli X errors. And I did that. And those Pauli X errors on that block, they're going to get copied onto the other codes through the CCZ, because the Pauli X errors I left behind, they don't commute with the transversal gate. And that's annoying, but it's not a problem so long as these errors stay nice and small. So, but again, we don't want to do this in 3 dimensions. We have a much bigger problem now, because what we have to do is we have to make a guess at what error has appeared given just the 2-dimensional slice that we have and the history that we've already produced. So let's give an issue where this might be a problem. So this is called just-in-time decoding, I should say, and this was an idea of Hector Bombin's. I don't know whether or not mine is the same. So I did this project because I was trying to understand Hector's paper, but rather than read it, I just reproduced it. So it's like this. Okay, so we've got this little slice, and time is moving upwards, and we see these 2 defects, and they're connected by some fairly long string. Now we have to make a decision, like, should we connect those 2 guys together? Let's assume an IID noise model. So the likelihood of those 2 defects being there is exponentially suppressed in L, if we assume a low error rate in IID noise. So it could be quite unlikely if that's a long error. So maybe what these defects correspond to is some error, like 2 strings where the defects just haven't appeared yet, and we were going to produce that piece of code. So we can just wait a little while. Rather than correcting them immediately, what we can do is we can just like extend the loop. We'll suppose the correction is going to go, we'll just correct upwards for a while. So we're going to make this loop a bit bigger before we actually correct it. And now we've gone a little further up in time, and now it's beginning to look a little bit more likely that that was the error after all, because we haven't found any defects. And well, finally, okay, you wait a bit longer, and then you say, okay, that was definitely the error that happened. And so we close them up. And so this is kind of bad, but if because we're going to make a correction that has a bigger loop than what would have been there if we had access to all 3 dimensions of information in one go. But yeah, maybe it's not a problem. Again, like the defects are going to be like exponentially suppressed in their separation. So maybe if we can feel confident soon enough that we need to correct these guys up, then yeah, the Pauli X's we leave behind with the slightly bad correction is going to be manageable. So it turns out all you need to do, like how confident do you need to be before you pair these guys up? So there's a rule. It's kind of technical, but like the rule is actually very simple. You're confident enough to pair 2 defects if both of the defects have waited for a time that's equal to their separation in space-time. They both have to exist for that long. So in this case, these 2 defects are separated by about this far, so if I wait about this far, it turns out to be fine. That's kind of easy to show, but I don't have time to do it just now. So this is the just-in-time decoder. It's just greedy. Like you could think of much smarter ways to do this if you're trying to do numerics, but I'm just really trying to prove that this can work. Okay, so the way I can prove that this works is using an error distribution, using some properties of an IID error distribution in the space-time. So this was all of this work, I learned all this stuff from this Bravi-Ha paper in the appendix of how they prove a threshold with the renormalization group decoder. So this has a long history. So in that paper, they cite Harrington, who did this for some cellular automata decoders, and then he was trying to reproduce the work of Gax and Gray, and then they got all their results from percolation theory, or at least that's how I think this all came about. Maybe somebody can correct me on that. So what they can show, they look at errors in terms of what they call the chunk decomposition. So a level n chunk, you define a chunk recursively. So a level n chunk is the disjoint union of two n-1 chunks that are suitably close together. And a level 0 chunk is just a single error. And so what you can prove is, if you look at connected components of these chunks, where a connected component includes a level m chunk, but not an m+1 chunk, then for some q that you're free to choose, some number q, then the connected components will be of size no bigger than q to the m, and separated from all connected components that are equal size or bigger by q to the m+1. So you have this big factor of q to play with in between level m chunks and other level m chunks or bigger chunks than that. Sorry, I mean connected components of errors, but I don't think we're not going to understand all the technical stuff by the end of this talk. So yeah, with this error configuration, these guys showed how to prove a threshold with the RG decoder. I use this configuration, but I need to do more work to make this work for the just-in-time method. So in fact, using that greedy method I proposed, where you compare defects after a time that's equal to the separation, well, because these are topological codes, the errors, the defects live at the endpoints of the errors. They're local within the neighborhood of the error. Well, all the defects that are created by a small chunk of errors are going to be corrected within the same distance. The furthest apart these two defects can be is about the size of this block. So all of the defects in this block are going to be grouped together after a time that's like proportional to the size of the block. So what happens when you run the just-in-time decoder is all the errors in these little blocks, they spread, but they spread by a factor that's proportional to the size of the block. And what's important is it's easy to see, if you just spend a little time with pen and paper, that big blocks aren't going to interfere with the little blocks too much. Or if they do, the little blocks are just going to kind of be so close to the big blocks that they'll just kind of get bound together. So this is roughly how you show that this gate has a threshold. You assume some noise model that's characterized according to, what I took from Bravi-Ha and references therein. The just-in-time decoder spreads all the connected components of this error by a constant factor. And as long as Q is large enough, the RG decoder will still clean up all the errors at the end, which you can actually do globally. You don't have to correct the spread errors in the end. You only have to do the gauge fixing just in time because you have to fix the gauge and do the CCZ gate and move on. Like the gauge has to be fixed before you do the CCZ gate, but once you've done the CCZ gate and everything's said and done, well then you can finally do a global decoding to see what errors really happened. Yeah, okay, and this is roughly a sketch of proof that this gate will work. I'm running out of time. How am I doing for time? I have like 5 more minutes, right? Okay. Great. So this all seems kind of bleak. So the threshold I got with this proof, well, it's a lower bound. It was 10 to the minus 15. I don't think it's going to be as low as that. I just put a really big exponent in there so the QIP guys would take me seriously as a theoretical physicist. And I thought that's how it worked. Now, so yeah, I'm running out of time, I guess. But you can mitigate a lot of these errors. It's going to be a lot better in real life. Because, so what would be smart? So I've said this is an alternative to magic state distillation or producing magic states, but I would still use this as a magic state factory. This gate would be the one component of a CCZ state factory. And the reason to do that is you can take a CCZ gate on your logical pluses that are easy to prepare fault tolerantly and make a CCZ gate. And while you've got this CCZ state, I said gate, I meant state. While you've got the CCZ state there, you can check. You can check to see your just-in-time decoder did what it was supposed to do, and that's really helpful. So what you can do, so all the qubits of this three-dimensional model are gone, like they were destroyed long ago, and you're just left with this two-dimensional slice at the end, which has had a CCZ acting on it. But what we can do is we can run a perfect decoder that had all 3 dimensions of information and see what it did, and just see if the just-in-time decoder got the right answer. And if it doesn't, well, we can just throw this CCZ state away without feeding a bad state into the computation. So this is good because even though the just-in-time decoder might not be as good as the real decoder, the decoder that has all access to 3 dimensions of information, well, if it's screwed up, we know about it, and it's not a big problem. So the only thing, if I were to try and use this as a magic state factory, the only thing that the just-in-time decoder's failure rate determines is how frequently do I produce CCZ states and how frequently do they screw up and I have to throw them away. But because this has a threshold, this is going to decay fast. If I'm below threshold, this is going to decay quickly with system size, with the co-distance. So yeah, with a large system, you'll never fail with the just-in-time decoder. And what's more, so let's suppose they do agree. So this is also an idea in Hector's paper. We know exactly where the just-in-time decoder put all the errors, because we know what mistakes we made compared to the good quality decoder. So what we can do is wherever there was an error, we can treat it as an erasure, and a known erasure because we know where it happened. So that's really great too, because actually topological codes have really high thresholds against known erasure errors. And so all these errors we introduce, they're not really stochastic at all. They're just, well, I don't think it's a problem. So yeah, so what I'm saying is, even though I got a very low threshold, well, a very lower bound on a threshold, the actual threshold I'm optimistic won't be too far off that of the real thing, the standard surface code where we're not having to do all these gauge fixing tricks. Okay, so I'm not going to do a conclusion slide. The question I'm going to get, or the 2 questions I'm going to get, is what's the catch, and what about magic state distillation? So for a long time, we've been working with magic state distillation. This original paper by Bravi and Kataev, it has like 800 citations. So like how many people has been optimizing this for 15 years is crazy. Like a lot of them are here right now. I'm not an expert in this at all. I haven't done research on it. So I'm trusting that Earl and Barbara and Christoph's review article covers all the major milestones. I read that. But I like this picture from this Gidney and Fowler paper showing over time the magic state factory steadily getting smaller and smaller, just how much work people are doing to get these things smaller and smaller. Like people expect that this is going to cost a lot of the quantum computer. So what's the catch? Well, look, I don't think it's so bad. It's going to be harder to build. It's going to be harder to build because we need all these extra ancillas kicking around to produce thin layers of 3D surface code. And we also have to intersect 3 surface codes on top of one another. The threshold's going to go down, but I'm optimistic it shouldn't be too much. I wouldn't want to stake any guesses on how much. And another trouble is we need a physical CCZ gate. So Shruti actually mentioned one of those, so that's kind of cool. But really, there's not many people have tried to build a CCZ gate, a 3-qubit interaction in the lab. And in fact, maybe this is the color code's chance to shine, because, well, yeah, as I said, all these ideas came from Hector by paper, where a paper by Hector, where he did a transversal T-gate, and there you only have to do a single qubit rotation, not a 3-qubit rotation. So even though the color code is typically a little bit worse because we have to do these weight 6 checks, it might catch up a little bit compared to the surface code because it only has a single qubit transversal non-Clifford gate rather than a 3-qubit one. But look, like magic states cost a lot of resources to do this circuit, like however you look at it. And here we just pass 3 surface codes over one another, so in principle, you hopefully don't need too many resources at all. And yeah, this is an exact gate too, so it'll improve and improve with code distance. And yeah, whereas if you want to do magic state distillation, you have to add more layers to the code. I know there are lots of tricks to make that not such a big deal, but growing the distance doesn't improve the logical failure rate of the gate. You have to add more layers as well, so the magic state factory has 2 parameters you have to scale to make it better, to the target failure rate. Yeah, so I am out of time, but I just want to show you this. So these are the main milestones towards this work, and what's really interesting is none of them have anything to do with the surface code, and a lot of them have things to do with Hector Bombin. So, so we came up with the 3D color codes, Hector and Martin Delgado, and they were kind of cool because they had a transversal non-Clifford gate, but people didn't want to build this because it had such high weight stabilizers and it was 3D. But then gauge fixing was introduced, and that's great because we found high thresholds with the gauge color code this way, and we were still able to do the T-gate, but it was still 3-dimensional. So then Hector showed us the colorful quantum computation that we heard about yesterday and a little bit in my talk just now. And yeah, so these ideas were also kind of there in the work of Rausendorf and his co-workers. And finally, the only reason all this work gets into the surface code is with all these unfolding results by Alex, so you should have waited to the end. Alex, and then this was simplified a bit by Dan and Michael. I chose their explicit construction, but these ideas were here in Alex's paper too. And also Hector introduced unfolding in 2 dimensions. So that's it. Thanks for listening. I'm sorry I ran over.
Thanks, Ben, for a very nice talk. Are there any questions?
Can you show again the picture where you sort of show the geometry of the sliding planes? So the question I have, if I cannot slide the patches, but have 3 patches sitting next to each other, what kind of connections do I need to implement this? Do I need fixed distance connections, or would it have to be both fixed distance and shifting distance connections to sort of?
So it's kind of fixed distance. So like all of these dynamics, I'm not really moving the code. The code deformations, when I produce a thin slice of 3D surface code, this is really moving these guys around.
So if I have L by L patches, all I need is connect qubits at distance L away, or 3 qubits.
Distance 1 or 2, like whatever your unit of length is in the cubic lattice, yeah. Yeah.
No. If I have 3 square patches, so instead of sliding them together, let's suppose I have a long distance CCZ gate, and so I need a bunch of parallel CCZ gates, taking qubit number 1 here, qubit number 1 here, qubit number 1 there, and all of these will be just shifted like a rigid structure, but and also simultaneously.
Yeah, that's right. It's local. I wasn't lying or anything. Whatever you mean by nearest neighbor or nearest neighbor. Like I don't want to say anything about nearest neighbor, but the interaction range is constant.
I have a maybe slightly related question. So when you have these like 3 planes sliding above each other, you made this analogy that you can think of it as like a small slice of a 3D surface code. Do you need the parity checks that you do, or the plaquettes that you do, to actually be 3D plaquettes, such that you do parity checks between the 2 layers? or you can just do the 2D checks?
No, you need to measure all of the plaquettes in the cube. Like that's important to do the gauge fixing trick, because otherwise you never learn the value of the full constraint about a cube. Yeah, but they're all 4-body or 3-body checks. In fact, so I should have mentioned as well, you never actually measure the stars directly. So you have quite high weight star operators. You actually infer the values of those when you collapse the code with X measurements. So that's kind of neat too. I should have mentioned, but the highest weight measurement you ever have to make is 4-body.
Okay, but it's 4-body between the layers.
Yeah, that's right. I'm producing a tiny piece, 2 by L piece of 3D surface code. That's right.
Okay, thanks.
So the 3D color code also has a transversal CCZ gate, whereas the 2D color code does not. But we know there's something in between, the so-called doubled color code that has a transversal CCZ as well and can be kind of unfolded and flattened into the plane. Does your construction with this sort of, just a constant width surface code imply the existence of like a doubled surface code that would have a transversal CCZ that you could similarly unfurl into or flatten into the plane?
I don't know. Like I know the construction of the double or the stacked or the color code. You have these big blue stabilizers in between, and you end up with no threshold. Maybe I don't really know. But I don't know why you would want that, because that won't have a threshold. Yeah. But maybe you have your own nefarious ideas.
Okay.
Let's take the last one.
So it looks like you're doing, 2 n time slices on this?
Or yeah, I would say 2D, but yeah.
2D, okay.
Yeah.
And so you're going to have non-uniform amounts of CCZs along each time slice?
Yeah, that's right. You want me to go to this slide?
Yeah.
Yeah, that's right. On the very first step, you just do one row, and then like there's only one point in the middle where you're doing full like L squared CCZs.
Okay.
Yeah.
Let's thank Ben again.